find out how to do the circuit sequence.
So hopefully people are listening in and can hear me. Usually when I get that feedback, they can hear. So did we get any feedback on sound check? No sound.
Yeah, we can hear.
Okay, good. All right, so it's going to be quite the competition between the class and online today. You're on the spot. All right, so today we want to talk about continuity. You have a handout on this. So I'm going to waltz through the theory on the handout, but really get to what we always do in here, the applicable equations. So the integration and the differentiation will go away, but fundamentally where we start is with the conservation of mass law, and the conservation of mass law that says for a system, and again, if you want to take a very simple view of a system, your bathtub can be a system. For a system, the mass volume out minus the mass volume in is equal to the change of mass over time. This actually has an error in it. I'm going to correct it real time. So this should have been in. That should have been in. Hopefully that's what's on your handout. And going back to this, so I just corrected it. Before it said mass out minus mass out, that wouldn't make any sense. So mass in, mass rate in, that's a true rate. So for example, kilograms per second minus mass out is the change in mass in the system over time. And again, think of your bathtub. And this can be applied to open and closed systems. So when we say an open system, again, think of your bathtub, a reservoir, a big holding tank for water. For a closed system, we're talking about systems that probably are already filled with the fluid. Think of a piping system, a plumbing system. So in the piping system, it's already filled with water, and you have a mass rate in and a mass rate out of that closed volume. And in that case, since the system's already filled with the fluid, if it's incompressible, then the mass in is equal to the mass out, because being incompressible, there can't be any change in mass over time in the closed system. Again, think of a pipe with water flowing in it. If it's a compressible fluid, like air, you could certainly have the pipe filled with air and more air going in than out. And what's happening is you're compressing the air in that system. Think of a basketball. So in your handout, we take these, and then we looked at a little differential cube, and we applied the mass flux laws to each side, in and out from each side. And what we arrived with were all these various equations. So again, this is the start of your handout. And for the start of your handout, there's two forms of the continuity equation, the differential form and the integral form. And I'll talk about the distinctions and ultimately how we use them. But in the differential form, you get this equation that basically says the density times the spatial change of velocity. So when we say velocity, velocity is a vector. And it's going to have, just like acceleration, components in the X, Y, and Z directions. And so what the differential form is saying is that the change of velocity in each of the directions times the density is equal to the time rate of change of density. Now that right-hand side, again, if you're an incompressible fluid, is going to go away, but what it's representing is that right-hand side is representing the change in mass. It's just when you look at the differential volume approach, dx, dy, dz, the size of the volume cancels on each side. So what we started out as mass flux in minus mass flux out now takes these curious terms, rho dv dx, rho dv dy, rho dv dz. And if you want to think about it, again, for a constant density fluid, or an incompressible fluid, as we would call it, the right-hand side would go to 0. Because again, if its density is constant, the differential with respect to x, y, z, or time is 0. And all the left-hand side is saying, again, think about something really simple. Here is an elbow in a pipe, and you're looking down on it. So you're looking into an XY plane. It's a horizontal plane. And basically you have the velocity vector coming in and the velocity vector coming out. And the velocity vector, again, has 3 components, Vx, Vy, Vz. What's happening when you go from the inlet to the outlet of this very simple elbow is the Vx has some tangible value here. And because this elbow, 90-degree elbow, is perfectly aligned with the x and the y, at the outlet, Vx is 0. So here you have dVx is actually going from Vx to 0. And similarly, at the inlet, Vy is 0. And it's some value Vy when you're leaving. And again, if it's in minus out, dV dx in minus out is Vx. For Vy, in minus out, 0 minus Vy is minus Vy. And what you basically have is dV dx equal minus dV dy. In this case, it's in a horizontal plane. The pipe walls don't allow any flow in the y direction. So again, it's a very, very simple analogy. All this is saying is, if you have a change in the velocity vector or flux in one direction, and somewhere else the flux is in a different direction, like through this elbow, everything's accounted for. That's all it really says. The other form of the continuity equation is the integral form. And basically what it says is, if we look at some location, we can integrate over the area density times velocity vector. And that will give us a mass flux. That should have a dot over it. Okay. That's all the integral form says. So your handout derives or basically presents these two forms. What I want to do is bring it into more of how we don't apply these. The differential form is more appropriate when you're looking at an entire system. And we're going to do examples of these. The integral form is typically what we use at a very specific location. And you can certainly combine these two concepts. You can be looking at a system and identifying what the flux is with flow at any one location, use the integral form. Although on the big scale, you're looking at a system and you're using the differential form. So here's systems and continuity. Here's a basketball. You can deflate the basketball. So you put the needle in the basketball, and here you have flow coming out. And what's happening as you deflate the basketball, you're getting less density, less mass inside of it. And that is all due to the flux out, and the flux of air going out is these terms. So that's all this is saying is, for this system, the system is the basketball, we have a change in mass, dm dt, in the basketball, and that's equal to mass flux in minus mass flux out. And in this case, there is no mass flux in, it's only out. Okay, so that's one way of applying the conceptual approach on the right-hand side, looking at the basketball, and that equation on the left-hand side, which looks now nothing like mass in minus mass out, but it was all reduced from that same concept. And the same thing applies when you're filling the basketball. Okay, In this case, you have a mass flux in, there is no mass flux out, and all you're doing is changing the density of the air or the volume of the fluid in the system. In this class, we don't spend a lot of time on compressible fluids. And so if we think of more of the type of systems that we use in fluid mechanics in this course, engineering fluid mechanics for particularly the civil and the environmental engineers. What we have, think of your bathtub again. And think of the fact that these equations came from looking at a system. The original system in your handout is a little cube. But again, that little cube can be expanded to this bathtub. And in this case, you have a flux in, the cold water. You also have another flux in, the hot water. And they don't have to be at the same rates. And if you have a leaky valve, or if you left the valve, the stopper on the bottom of the bathtub open, you would have a flux out. And in this case, you have mass flux in represented by Q1 and Q2. Mass flux out represented by Q3. That's what's going through the drain. And the right-hand side, the change in mass over time, is basically how the water level is changing over the area, the surface area of that tub at any given time. And yes, the surface area can change with elevation, but basically that's how we're applying the differential form of the continuity equation to a system. In this case, what is the system? The system is the inside of the bathtub, okay? And so we define that system as the inside of the bathtub. And what we see is we have these fluxes that leave the system boundaries. And this is actually a pretty important component because in a few weeks, we're going to talk about momentum. And I'm going to basically use this as an analogy. And what we see is when you look at the externalities, the sum of all externalities, what are the externalities? The fluxes crossing the control volume boundary. So the inside of the tub, we refer to as a control volume. It's usually just some mass of fluid, which we're trying to study. And we say that the sum of the elements crossing the control volume boundary is equal to what's happening inside the control volume. Sum of externalities is equal to what's happening inside. Again, just think of your bathtub. You've done this probably dozens of times in your sink or a bathtub or filling up some container with fluid. And all you're doing is playing the continuity equation. So here's a simple example of that analogy. To control floods, typically, question?
Yeah, I have a question. In that last example, would the density change?
Pardon me?
Would the density change in that bathtub example?
With the depth?
Yes.
Yeah, so H was representing the change basically in the depth of water, but we were just looking at right at the top. So if you look at, the question was, does the depth change? So if you look at the depth of water as being H, what I wrote up here is dm dt is equal to density. I factored out density times the change in volume with time, dv dt. And the change in volume, I'm going to say, let's say instead of this nice smooth cornered bathtub, we basically have what looks like a rectangle of brick. And so we can factor out the cross-sectional area. And that leaves us with the change in total height versus time. And if I put that change in total height versus times as a delta H, that would be H1 minus H2. And that's the DH that we're talking about over there. So absolutely the depth of flow changes. And as we'll see later, when the depth of flow changes, that actually is going to affect Q3. And you know that. If you had a volume of a container and you poked a hole in the side, the flow is highest as soon as you poke the hole, and as the water level decreases, the flow out of the side of that hole decreases. We're going to derive that after we go through energy equation, and that's called the Torricelli equation. But there is a way to describe that, and again, it's something you already know from your experience. So we were talking about just looking at a system, and in this case, our system is a reservoir. So it's how we control floods. So when a big flood comes, what we typically do is try to put water into storage, which means what we've done is to keep behind a dam somewhere a space evacuated that we only use to store water for floods. So typically behind a dam, there's different zones. The lowest zone is a volume when you build the dam, it's reserved for maybe filling up with storage, with sediment. A lot of times that's called dead storage. And then there's an intermediate zone that you're filling and draining, and that's the water you're using. It could be for irrigation, it could be for hydropower, it could be for drinking water supplies. And that actively used storage is known as working storage. And then above that is a zone you typically leave empty, and that's for flood storage. And so here you have a reservoir, and it's at some initial water surface elevation. Let's say it's right here. And what you have is this inflow of 4,000 cubic feet per second. And over the top, over the spillway, we have 1,000 cubic feet per second leaving. And through the hydropower turbines, we have 400 cubic feet per second leaving. So I think easily you can see with 4,000 coming in and only 1,400 leaving, you must be putting water into storage. This is exactly what we do for flood control. And then the last question is, the first question is, what's the volumetric, that should be rate. What's the volumetric rate of change for the reservoir? So that's basically saying difference between inflow and outflow. So we started with this. If we have a constant density fluid, and so again, with liquids, we typically assume for most of the pressures we work at in engineered systems that the fluid is incompressible, the liquid is incompressible, water, for example. And so when we say an incompressible fluid, we're saying basically in this system, the density is going to be a constant. And we can factor out the density from each of these terms. And for example, Mn is the density times the volumetric rate N. And for volumetric rate, we usually use capital Q. So density has the dimensions of slug, for example, per cubic feet. That's density is mass per unit volume. And volumetric discharge is volume, say cubic feet per second. So a mass rate would have the dimensions of slug per second, whereas a volumetric rate would have the dimensions of volume per second. So in lab 2, you are calculating volumetric discharge in gallons per minute, cubic feet per second. So going back to the continuity equation I drew at the bottom, if we factor out density, what you have is Q in minus Q out. That would be all of the Q ins. So it could be happening in multiple locations. All of the Q out. Again, everything external that's crossing the control volume boundary. What's our control volume in this case? It's the evacuated space in the reservoir where we're putting all the floodwaters into. And this would then be equal to the change in the volume of the reservoir, with time. And that's what's being asked. What's the volumetric rate? So all we would need to do in this question is sum inflows, subtract all the outflows, and that would give us our volumetric rate. The next part of this question is, if we have a reservoir surface area of 3,000 acres, what's the rate of change of the water surface in 1 day? So our inflows, there's only one. It's on the upstream part of the reservoir. It's where the river's coming in at 4,000 CFS. We have two outflows. One is going over the spillways on the top of the reservoir, 1,000 CFS, and the other is going through the hydropower penstocks, 400 cubic feet per second. So the volumetric change would be the inflows minus the outflows. And again, this is the equation I had on the previous page that I hand wrote in the lower left-hand corner. And again, you have to look at these. If you're looking at discrete locations, you could have multiple locations where everything's coming in. Q in represents all of the Q in, Q out represents all of the Q out. So we had 4,000 in, and then two locations of outflow, 1,000 cubic feet per second over the spillway, 400 through the hydropower turbine, and that would give us 2,600 cubic feet per second. That's the volumetric rate of change. Now, if we wanted to convert it, there's 43,560 square feet per acre. And there's 8,600 seconds per day. And so we can convert cubic feet per second to a more common unit that we typically use. AF is acre feet. So again, we would take the cubic foot per second, divide that by 43,560 square feet per acre, and that would give us acre feet per second, which would be a really small number. So then we multiply by 86,400 seconds per day, and that gives us acre feet per day. So that was the first question in this example. What's the volumetric rate of change? If you maintain these flows, 4,000 coming in, 1,400 leaving for a 24-hour period, you would have a rate of change of 5,127 acre feet per day. If you only maintained this scenario for 1 hour, your rate of change is still 2,600 CFS, but only for that hour. If inflows are changing, and that's what typically happens, the inflow is not always constant. It's a hydrograph, and you have a rising limb and a falling limb. And so you would apply this continuity equation for time steps or time intervals. For example, every 10 minutes, every 1 hour, every 24 hours. That's how we actually do reservoir operations. Any questions? Okay, so continuing, the second part of this question was, what's the rate of rise in 1 day? So we just calculated the right-hand side, the volumetric rate of change. That volumetric rate of change, is the surface area times the incremental elevation change or height change, delta H. And this question, what's the rate of rise in 1 day, is prescribing delta T. Delta T is 1 day. The area was given. This question is asking for delta H. What's delta H in 1 day? So we solved the equation above algebraically for delta H. And so in this case, the rate of rise in 1 day is the volumetric rate of change, which we said was 2,600 CFS or 5,127 acre feet per day. Delta T is prescribed 1 day, and the surface area is 3,000 acres. So that would give us a rate of change of 1.71 foot per day. So again, if you maintained these conditions for 24 hours, that reservoir would have increased the depth by 1.71 feet. So if it started at 30 feet, it would be 31.71 feet at the end of the day. Again, if you only maintain this condition for 1 hour, then that rate of rise, 1.71 feet per day, is still accurate, but it only did that for 1 hour. So if you divide that by 24 hours per day, you would see the rate of rise in that 1 hour period. Okay. So blank slides means I didn't have time to make them before class, so here we are. We're going to look at, for example, if we have a population, like all of the students, think of the days back on campus. You wake up in the morning, 10, 11 a.m., everybody's flushing the toilet, taking showers, you go off to class, you come back for lunch. And so you might have a demand schedule. We call it a diurnal demand, but typically there's 2 peaks per day, one in the morning, a smaller one in the middle of the day, but one in the evening at the end of the day. So for example, this might be midnight and noon is typically somewhere in here. And again, midnight. So this is morning. And this is evening. So that is how we're using water. At a water treatment plant, you don't have someone there opening and closing a valve. The easiest way to operate systems, especially engineered systems, is to have them operating constantly so that everything's the same. All the flows are the same, all the water chemistry is the same, all the energy use is the same. So typically what happens is, if we also look at the supply, and that supply, again, could just be from a groundwater well. It could be from a water treatment plant. The supply is the dashed line, and the demand is the solid line. And so we might have ground storage tanks. So there's 3 of these in Durham. One is kind of behind Greg Hall in the woods over near where the water treatment plant. The other is over by the Alumni Center. And then there's another tank over by Route 4 where the telecommunication tower is on Beach Hill, which is also a nice mountain biking place. So you have these tanks, and at any given time, you have a water level in the tank. And what's happening when demand exceeds supply? You're draining the tank. And at the times when supply exceeds demand, you're filling the tank. And so what we typically use is storage to even out demand, to equalize, or it's known as equalization storage. And we use that in a lot of engineered systems. So this is an example of, for example, drinking water. You could look at the same thing for stormwater. In a stormwater system, we may have, for example, a detention pond or a bioretention system. And in stormwater systems, we'll have an inflow hydrograph. And that's what's running off the land, all the parking lots, all the rooftops, all the sidewalks. And we may have required maximum or limits on how much runoff we can have from a site. That's really common. We typically limit the runoff to not to exceed the pre-development runoff peaks. And so what we'll do is we'll build a detention pond, or we'll put in some other device where we can temporarily store water. And so what we'll do is, when we build that, we can have, just like your bathtub, inflow and outflow at the same time. When inflow exceeds outflow, you're filling the system up. And then there will become a time when the inflow gets lower and lower and lower and finally ceases, where outflow exceeds inflow, and now you're draining the system. So this concept we used in example 1, we use for an incredibly limitless type of design facets. And our designs are all the dimensions that have to do with this, as well as estimating each one of these temporal histories, the demand history, the supply history, the inflow hydrograph, the outflow hydrograph. Okay, so all of that was talking about the differential form of the energy equation. And you saw in that example, I did not use any derivatives and I did not use any integral calculus. It's just looking at a system, inflow, outflow, change in volume over time. When we look at the integral form of the equation, which I have here, basically what we're doing is saying we can get at one location, think about the cross section of a pipe or the cross section of a river. We can get at that location the mass flux rate by integrating over the cross section the product of density times the velocity vector. If we look at that integral and we assume that one, we have a constant velocity field. Well, if it's a constant, it comes out of the integrand, right? If we also assume a constant density or incompressible fluid, that would be a liquid. That means the density would also come out of the integrand. And so what you're left with is density times area, integral over the area of dA, which is rho, oops, I did that wrong, it should be V. Rho V A. And that's what you see as the first bullet here. The mass rate flux at a cross section is equal to the density of the fluid times the one-dimensional or constant velocity field times the cross-sectional area. So here's a pipe. And when I draw a pipe or the end of a pipe that looks like this, all I'm indicating is that I cut it away from the rest of the system. So this pipe is continuing in both directions, left and right, and we're just looking at this piece. And so what we're saying is, if we look at the cross-section A, in this pipe, we have a constant velocity vector. It's all across the cross-section constant. And again, in one of your labs, you're going to see this isn't true. But again, this is just a very simple assumption. What we call this one-dimensional velocity vector would be the average velocity. And how we would find it is to take the total volumetric discharge and divide by the cross-sectional area. So again, the mass flux rate, m dot, is density velocity times area. The volumetric flux rate, like flux capacitor, would just divide the previous equation by density. So in this case, the volumetric discharge is velocity times area, and that's how we, again, can calculate average velocity. If we substitute that back into this equation, mass flux rate is density times volumetric discharge. And then lastly, we could take the first equation, the mass flux rate, and multiply both sides by the acceleration due to gravity. You know from your experience that specific weight is density times acceleration due to gravity. And so we can also calculate a weight flow rate. And if you recall, in the lab 2, the first lab you had in the fluids lab, you had water pouring into a horse tank that was on a scale. And what we did was we started a clock when there was a certain water level in there, and we had an initial weight of water. And then we put on a weight on a scale and we measured the time it took for the scale to equal that weight of water. And so we took that weight of water and divided it by the time, and that gave us a weight flow rate. That's what we did in the first lab. And if we took that weight flow rate and we wanted to calculate, for example, the flux rate in the channel, capital G, the weight flow rate, is gamma VA, which is gamma Q. So that just means that the volumetric flow rate is G divided by the specific weight. And that's what you did in the lab. That's what you're asked to do. You come up with a volumetric flow rate. So again, continuity using the integral form is typically used at specific locations. And previously, I said you can mix those two together. So for example, if you think of a control volume, again, your control volume could be a bathtub, could be a reservoir, could be a water tank. You could use the differential form for the system, but in any one location, you could use this integral form. Q is equal to VA, for example. And I'm going to do some more examples. So for piping systems, again, we just established for the piping system that the discharge is velocity times the cross-sectional area, and that velocity is a one-dimensional or a cross-sectional average velocity, and A is the cross-section of the pipe. And you have to understand, we're just talking about the fluid. So when we say the cross-section of the pipe, it's the inside diameter of the pipe. So when you hear something that says it's a 6-inch pipe, that's not actually the inside diameter of the pipe. That's what we call the pipe. The inside diameter is something close to that. And we're going to get into that in future lectures. For now, when you hear it's a 6-inch diameter pipe, you are to assume that that's the inside diameter, or ID as we call it. So, second example. What's the steady state velocity in a water pipe where the diameter is 10 inches if the discharge or the flow is 800 gallons per minute? And again, this is using this integral form of the equation. So first thing, you know there's 7.48 gallons per cubic foot, and you should also know there's 60 seconds per minute. And if we multiply those two together, basically there are 448.8 gallons per minute per cubic foot per second. So again, why do I do this? We work in either SI or BGS. SI, the units dimension should be meters, seconds, kilograms, and newtons. And in our system of units, we have foot, pound, second, slug. So gallons per minute is neither of those. So I'm converting gallons per minute to our BGS units, feet and seconds. So the 800 gallons per minute, again, from this conversion is 1.78 cubic feet per second. Because I'm after a velocity, and that velocity is going to have the dimensions of velocity length per time. So again, we have, I think I have it next. There it is. V is equal to Q over A, and that came from Q is equal to VA. And the dimensions on there that are foot cubed per second on the left-hand side. And then you have foot or length per second times foot squared. So again, it's all dimensionally consistent. So up above, the pipe cross-sectional area is pi over 4 d squared. And that converts to 0.545 square feet. The velocity is then discharge over area, 1.78 cubic feet per second, divided by 0.545 square feet, and the velocity is 3.27 foot per second. Okay. If you were asked what is the weight flow rate, the weight flow rate would just be the specific weight of the fluid. We said up above it's water. So we would take the 62.4 times the flow rate of 1.78 cubic feet per second, and that would give us 111 pounds per second. As you can imagine, 1.78 cubic feet per second of water is a lot of water. 800 gallons per minute is the kind of flow we use to fight fires with. This is a lot of water to move in a piping system. It's minuscule when you're talking about rivers. And then if you were asked about what's the mass flow rate, the mass flow rate, that should have a dot over it, is equal to rho Q. And rho in this case is the density of water, 1.94 slugs per cubic foot, times the discharge rate, 1.78 cubic feet per second, and that gives us 3.45 slugs per second. Again, that's all our system of units, British Gravitational System, BGS. So again, that's how we would look at it at one location in a system. In this case, the system was a pipe. When we talk about, or when you hear steady state incompressible flow, steady state means at one location, velocity, pressure, and the discharge, the flow, are time invariant. So for example, at this location in a pipe, that velocity is the velocity now, 10 minutes from now, 200 years from now, time invariant. In addition, the pressure at this location and the discharge at this location are all time invariant. That's what steady state means. And then lastly, when we say it's incompressible, also at that location, the density is time invariant. So the density, by being incompressible, is also not a function of pressure. So for gases, that's not true. In general, gases at very low velocity, for example, in the ductworks of buildings, sometimes can be assumed to be incompressible. That's not an uncommon assumption when you're designing HVAC systems. For piping systems, again, at various locations, if you have a single pipe, the diameter can vary. So we're coming down and then we increase the diameter or we decrease the diameter. So when we say the diameter in a single pipe is changing, we're talking about either an expansion or a contraction. If you have steady, incompressible flow, then the discharge everywhere in that single pipe is the same. By being incompressible, you can't have more water going into the pipe than leaving the pipe. That doesn't happen. In most engineering applications, there will be a very selective case I'll talk about. We won't study it in here. We talk about it in the advanced course, design of water transmission systems. But so in this case, if the discharge is constant everywhere, we can have these different diameters. And obviously, if the cross-sectional area is changing and the discharge is a constant, then what must be happening as we move through the system with changing diameters is that the velocity must be changing. So is it an expansion or a contraction? Has everything to do with which way the flow is, right? So if the flow is to the left, oops, left. One thing you're going to learn quickly, I'm dyslexic with left and right. So flow to the left, in this case, that would go from a small diameter, D2, to a larger diameter. That's an expansion. If we have flow to the right, that would be a contraction. You're going from a large diameter, D1, to a smaller diameter, D2. So it looks the same, has everything to do with which way flow is going. Whether you're looking at the expansion or contraction, this continuity equation is true. It doesn't matter which way flow is going because you're applying it at different specific locations. And this is what we're going to need when we move into the next two sections, energy and momentum. We're going to need to be able to calculate how velocities can vary through systems. So in the third example, the remaining time, we have a pipe expansion. The discharge is 200 gallons per minute. We've got the entrance to the pipe expansion of 2 inches. And then the exit is 4 inches. Okay, and so it's an expansion, so flow is going from the smaller diameter to the larger diameter. And so the question is, calculate the velocity at the entrance, D1, and the velocity at the exit, D2. from our continuity equation, we know that the discharge is steady incompressible flow. That's what we work with in this course almost all the time. And that just means at any location, the velocity times the area is a constant. That's the discharge. In this case of the expansion, what we see is the areas are changing and therefore the velocities must be changing. So we can take the continuity equation at each location, Q is equal to V1A1 and Q is equal to V2A2, and rearrange them to solve for V1 and V2. We know the discharge, we know the diameters, so we know the areas. The other thing we can do is take the two velocity time area portions of that equation, and we can solve for one velocity in terms of the other. But to use either one of those two equations, we would have necessarily needed to use that equation first. Because here you have basically one equation and two unknowns. Same thing here. So by using this equation once, we get rid of one of those unknowns. You can certainly use both of these equations or shift to the other one. You get the same answer. They all came from the same place. So 200 gallons per minute. We're going to convert that to cubic feet per second. So we divide by 448 gallons per minute per cubic foot per second. And that gives us 0.446 cubic feet per second. That's the discharge. It's the same at any location in this expansion. We then take the discharge divided by cross-sectional area 1 in order to get the velocity at 1. The discharge we just calculated to be 0.446 cubic feet per second. Cross-sectional area of a circle, pi over 4d squared. And you'll see that I converted from inches to feet for the diameter. And so at location 1, we have 20.4 foot per second. And instead of using Q over A2 is equal to V2, we jump to the other equation. Either of those will give you the same answer. And so in this case, what you see is the velocities are proportional to the diameter ratio squared. So in this case, we doubled the diameter, so we should reduce the velocity by fourfold. I'm going to put a 0. I just wrote Q is equal to V1A1 is equal to V2A2. I'm going to put a 0 above the Q. What do I mean by that? It's not changing. As we move through the system, Q is not changing. And so when we go from V1 and A1 to V2 and A2, what's happening? Well, A2 is increasing. In order to have the discharge constant, V2 had to decrease, right? So basically this increased and that decreased. And as you see, when we're looking at circular pipes, it's proportional to the ratio of diameter squared. And there's a reason why we do things like this. See, is that it? Yeah. So I posted a handout for you on energy. Bring those next time. I will have some in class. You can read through it. It may look more Greek than English to you, but I'm going to walk through that next class when we go through energy. But when we have really high velocities, what we're going to see is that translates into high energy losses. Sometimes we want that. So when we take water from the western slopes of Colorado and move it to the eastern slopes to feed Denver and all the Front Range towns, you have water starting at maybe 8,000 to 10,000 feet, going down to 4,000 feet. And that will come at a very high velocity. And what they try to do is break the velocity with friction losses. Nowadays, they're replacing all that and generating power from it. And so typically in distribution systems, what we try to do is minimize velocities. And by minimizing velocities, you can move water over enormous locations, cities like Philadelphia, Pennsylvania, New York City, Boston. By keeping the velocities really low, you're basically just using pressure to move fluid around. And that's what we're getting into next class. We're talking about energy, and this is all going to come to head. There's 3 laws to fluid mechanics. We just finished the continuity equation. The other 2 laws are energy and momentum, and we're going to do energy next week. So I have a few seconds left. Are there any questions? I hope to schedule a review session for later next week sometime. And again, what we did before was put it late in the day. So for example, I could make it Thursday. Supposedly Fridays from noon to 5 are common exam time. So there aren't supposed to be classes then. And so I might shoot for Friday afternoon. And I will post a request first to let me know if anybody has a challenge with that. I know I can't please everybody in this class. I'm just looking for the one time where I can get most of you who might want to show up. It'll be a Zoom Zoom setting where you can just ask me any questions about the homeworks. So any questions? Then have a great weekend. We just reached mid-semester, which is pretty amazing. That I think from here on out, we have only 5 more weeks of classes this way, and then it all moves online November 20th. Enjoy the weekend.
Okay. Is that